Welcome to Homework Lib.
We're going to be dealing with phosphoric acid, which is going to have different Ka's, so Ka1, Ka2, and Ka3. In this case, it's going to be enough to consider only the first pKa, which corresponds to a Ka of 7.5 times 10 to the minus 3. The second one is 6.2 times 10 to the minus 8, and the last one is 4.8 times 10 to the minus 13. So this is going to give us different values for pKa for each of the acid-base equilibriums. And the values for pKa are going to be, for the first one, 2.125. For the second one, is going to be 7.2. And for the last one, is going to be 12.32. So in this case, we're going to be dealing only with the first pKa because we know that a solution of phosphoric acid in water is going to likely only going to have abundance within the first pKa. It's going to be hard for the transformation for the second reaction of Ka2 in order to generate the HPO4 species. So with this, the reaction that we're going to be interested in is going to be considering that the concentration of H3PO4 in a cola drink is going to be equal to 0.007 molar. And we're going to only consider the second reaction if the pH that we find is of around 6. If the pH is lower than that, then we're safe with our approximation. Okay, so that means that our reaction is going to be equal to H3PO4 plus water. That is going to produce H2PO4 minus plus H2O plus. The initial concentration that we're going to have is going to be equal to 0.007. We're going to assume that we're going to begin with 0 of each of the other species, and of water it doesn't matter because it is going to be a condensed phase. So the amount of change is going to be minus x of the phosphoric acid and plus x on the other two species. So we're going to have 0.007 minus x, and x. So the value for Ka, which is equal to the concentration of Ka1, that is equal to the concentration of H2PO4 minus times the concentration of H2O plus divided by the concentration of H3PO4 is going to be equal to x squared divided by 0.007 minus x. Notice that this is going to be equal to 7.5 times 10 to the minus 3. So in this case, it is not going to be sensible to do the approximation that we usually use in chemistry whenever we're dealing with the acid-base equilibrium, which is going to be the small x approximation. In this case, it's not going to be valid because the value for the equilibrium constant is not going to be small enough for us to give a correct result. So we are going to need to solve the full quadratic expression. So this is going to become x squared is going to be equal to minus 7.5 times 10 to the minus 3 x plus 0.007 times this value, which is going to give us 5.25 times 10 to the minus 5. Thus, this quadratic expression becomes x squared plus 7.5 times 10 to the minus 3 on x plus 5.25 times 10 to the minus 5.25 times 10 to the minus 5 equal to 0. So the solution from this equation can come from either your calculator. You can apply directly the general formula, that is minus b plus minus square root of b squared minus 4 times ac divided by 2a, where b in this case is a is going to be equal to 1, b is going to be 7.5 times 10 to the minus 3, and c would be minus 5.25 times 10 to the minus 5. So you can apply either approach, but the results for x1 and x2 are going to be, the first one is going to be a negative value, which is 0.0119, and the second one is going to be a positive value, which corresponds to 0.00440858. So the positive value is going to be the correct answer over here, because it's the only one with physical meaning. And remember that from our from our ice table, the concentration of H2O plus is going to be equal to X. So since the concentration of H2O plus is equal to X, then the pH, which is minus the logarithm of this concentration, is going to be equal to minus the logarithm of X for us. So the logarithm of this value is going to be equal to 2.3557, which we can round up as 2 point, a pH of approximately 2.4. Since the value of the pH is not going to be high enough to consider the next chemical reaction, then we're good to go, and this is going to be our final answer.